Hi guys. So you should have or need to get out right now your study guide that had this on the front. We already filled out this first one. So we're going to be going to the next one that says oxidation. And I'm just going to point out a few of the main ideas and kind of what we're looking at here. Okay, so example 1. Okay, anytime you have a neutral element or a molecule made of only one element, oxidation is always 0. Okay, if it's not an ion, it's made of one element, its oxidation is 0, and we put the number right above it. Not over here, right above it. Okay, so, and also remember when we are doing oxidation numbers, the sign, as in the plus or the minus, goes before the number. Okay, so like for example, I've got a couple here. Okay, so NH3 given as a neutral molecule, no charge. So at my total line, I keep a track here, the total is going to be 0. Hydrogen is one of my shortcut elements. It's going to be +1. And I have the plus before the 1, and it's right above the hydrogen. It's not over here. This is where I would put a charge on something. The charge of an ion, oxidation numbers go right above, sign, and then number. So the total of +3. So then the -3 has to go to perfectly counterbalance the +3. There's only one element of nitrogen, so it gets all of the -3. But if you're finding oxidation of an ion, so this would be the ammonium ion, one of our polyatomic ions, then instead of adding up to 0, it will add up to the charge. So since ammonium is a +1 charge, the sum of oxidation is +1. We can still go back, start with a shortcut element, hydrogen's +1. I have 4 of them, so I have a +4, but now instead of -4, to add up to 0, I only have -3. So you see both of these elements, their oxidation is actually unchanged, whether it is the neutral molecule or the charged NH4. Same idea. Right, so remember our special rules that are handy shortcuts. Fluorine is -1 unless it's neutral molecule, which would have an oxidation of 0. Hydrogen shortcut +1, unless it's with a metal ore, as a plain old molecule, and oxygen, error here, -2, unless an H2O2, or as a plain old oxygen molecule. Okay, so here would be another example. We have H3PO4. Oxygen's a shortcut molecule. -2 times 4 is -8. Hydrogen's a shortcut element. +1 times 3 is +3. They have to add up to 0, so the +5 comes from, that's the only number I could put there. That would make the equation true and add up to 0. Since there's only one phosphorus, all of that +5 charge is right here. So again, for oxidation, put the plus or minus in front of the number and put it right above the element symbol. Alright, this is at the bottom of that same page. I did notice that that 2 is missing. So this would be NH4 in parentheses 2. And we're trying to find the percent composition. I'm just going to go through the second example. The first one is very similar. Okay, so first thing, anytime you're finding mass composition, is we need to know the mass of the whole thing. Okay, so we're pretty good at doing that. So it would be the mass of 2 hydrogens, 2 times imaginary 1, 2 hydrogens, plus the mass of 8 hydrogens, 4 times 2, 8, plus the mass of a sulfur. So Mrs. B, go and pause this and let them try and find that. Once they've found it, we'll see it is, hopefully, 68.138 grams per mole. Remember, just like any kind of percent, to find percent of the elements, it is the mass of each element in the compound or in the formula divided by the mass of the whole thing. So since I'm not there, All I can do is show you and give you time to make sure you understand where the numbers came from. Okay, so mass, composition, percent composition. Again, I recommend doing a row for each element. So I've got nitrogen, the mass of the 2 nitrogens on the top, because there are 2 nitrogens in the formula, divided by the mass of the whole thing, times 100. So that will give me the percent mass of nitrogen. If you do the same thing for all 3 elements, they should, fingers crossed, add up to 100. If they don't add up to 100 when you're done, probably you want to go back and double check something. If it's off by maybe just 0.1, like it's 99.9 or it's 100.1, it could be rounding error, but this is the best way to find these. This is the very last slide of that packet. I'm skipping to this because there's at least 1 or 2 on the Khan Academies that you're going to do where you want to be able to do this. So on the previous slide, we will tomorrow go back and figure out why it's N2O5, but that's the empirical formula. So we're saying if something's empirical formula is N2O5, but we are given that its actual mass of a formula is 216 AMU, remember we're going to figure out how many times bigger is the real molecule than the empirical formula. Okay, so we have how big is the actual formula compared to the mass of just the empirical formula. Okay, so if you pause this and go find the molar mass or the formula mass of N2O5, you'll see that it's about 108. So it ends up 2. So remember what that 2 is telling us is that the real formula of the actual molecule is twice as big as our empirical formula. So the true formula is twice as big as our empirical formula. So instead of 2 nitrogens, we will have 4. And instead of 5 oxygens, we will have 10. And that would be the actual formula if the formula mass is 216, because it's twice as big as the mass of the empirical formula. Alright, with the rest of the time, there are 3 Khan Academy tasks assigned to you. I would do them in this order because that would be escalating difficulty. I think you'll probably have time to get through them right now, but if you don't, they're going to be due Tuesday at 4. That way, if you get stuck, you can ask me questions tomorrow. Remember, do them as many times as you want to till you get the grade you like. Be sure to screenshot a screenshot that shows your name and your scores and attach that to the assignment on Classroom. Alright, see you tomorrow.